Okay. Step. Okay, so let me recall what we did in the last lecture. So for the last lecture, we talked about mirror or kind of say homomorphism theory or varieties. And our mirror was formulated in the following way, that here we have like toric X, and it corresponds to the theory on toric X. And here mirror is what is called Landau-Ginzburg theory. Cycle theory, which was collection of the following data. So let's say we have complex dimension of X equal to capital N. So we have kind of our target space or some space where we have functions. It's C star to the power n, kind of algebraic torus of complex dimension n. So then this space is actually like non-compact Calabi-Yau, so it's endowed with some non-degenerate top form. So then we have mirror superpotential that is kind of uniquely determined by toric variety X, so that's why it carries subscript X. And we have additional data which is good section, and that's kind of the reason why we have this additional words cited. So usually Landau-Ginzburg model is kind of referred to that part, kind of model with a superpotential. So, and our, let me do it. So our kind of simplest example this subtraction is X equals P1, and the corresponding Landau-Ginzburg model, so capital N equals 1, for kind of LGS model has space C star. And on this C star, okay, so there are two types of coordinates, so we can either treat C star as C with 0 removed, with the coordinate. So, and removing this point means that Z is non-zero. So then, in this notation, our holomorphic top form is dV over Z. So we can divide by Z, and hence, because we remove Z equal to 0. And then, kind of mirror superpotential for P1 in this coordinate is just Z plus Q over Z. And that kind of good section is spent by identity and so that is our data, and that's kind of the usual form of mirror superpotential that we see in the literature. So, however, for kind of proof of this relation using tropical geometry, it is more convenient. So we choose coordinates. So we do a coordinate transformation Z equals to e to the iy. So that simplifies the top form drastically. So top form became just I dy. So kind of very natural top form, like no kind of coefficient in front of dy. So it's a top form with constant coefficient. So mirror superpotential became something with exponential superpotentials, and kind of image with good section is now spent by by identity and 2 to the minus 5. So that's kind of why coordinates are more kind of conventional for kind of future proof. So that's why we will kind of gradually go from these coordinates like coordinates on C used in the literature to these coordinates that we used in our papers, and that's kind of more natural to describe C. Okay, so and on the left hand side, kind of we have 4 collections. Okay, so on the left hand side, so that is kind of mirrors of theories. So on the left hand side, we have kind of observables. So it's some collection of cycles or Poincare dual forms, or just cosmology classes on X. And these observables, they are mapped to the following things. So we have a good section, and okay, so let me do it this way. So cosmology, let's say phi A that belong to, let's say, image of, say, classes of phi A and classes of phi A, these kind of elements of Jacobian. Okay, let's do it. I'm working. So let's do it as a relation between classes. So phi A classes in Jacobian, which is quotient with this space of functions on this algebraic torus, molded by gradient ideal that is constructed from partial derivatives of this data. So that's it kind of observable. So here we have like some collection of cosmology classes, and on the right hand side we have collection of classes in this quotient space, which are just holomorphic functions on C star to the power n, modular shifts by elements of this gradient ideal. So these classes, they essentially like holomorphic function up to kind of arbitrary shift, and it's just arbitrary holomorphic vector field. I don't know how to call it. Vector holomorphic vector. So it's arbitrary function, and then we shift by vector field, holomorphic vector field applied to this holomorphic function. And kind of using these observables, we can compute some interesting numbers, and we can actually combine these numbers into polynomials with integer coefficients. If we kind of sum up Gromov-Witten invariance in zeros, Gromov-Witten invariance, so we kind of combine them like the invariant with the same observables. We kind of combine invariants of different degrees by summing up over this positive part of second homologies. So that are some polynomials in Q. Polynomials in these variables Q alpha with integer coefficients. So integer coefficients are Gromov-Witten invariants, and we kind of package it certain Gromov-Witten invariants with the same collection of observables, and these expressions, they actually equal to the following expression. So it's equal to correlation function of this phi a1, phi an in Landau-Ginzburg-Saito theory with a mirror superpotential. So here, like Q dependent, so both like these good sections for these classes, they Q dependent, and W is Q dependent. So and here, like, it's rather non-trivial that the right hand side is also polynomial in Q, because from procedure and from kind of construction of residue formula, it's not entirely obvious that the right hand side is polynomial in Q, but it happens to be that it's also polynomial in Q, and mirror for toric is just relation of two polynomials. Depends on Q.
Yes. Why this polynomial with integral?
Because Gromov-Fit invariants, they have enumerative meaning. So if you define it as a bracket like this with kind of integral over modular space, then it's just like complex numbers. But then there is like a enumerative problem to which the Gromov-Fit invariants are answers. So they actually count the curves with a certain property. And as answer to a certain counting problem, it is an integer number. So
in general, it can be irrational.
If you don't include descendants on a toric variety, no, it's always integer. So if you include descendants or go to higher genus, like genus 0, Gromov-Fit invariants of toric variety, that's integer number. That's for sure.
Okay.
So if you relax, say, consider genus non-zero on a toric variety, then it is a rational number and it can be negative number. And we will see like some example that in this example, let's say remark. So if I look at 1-point function, which is just gamma p, but for genus 1-point function. So this one is kind of it's 1 over 24. So for genus 1. Like even without descendants, you can get you can get like rational numbers and even negative numbers. And similarly, if you allow for gravitational descendants and consider genus 0, you will also have rational numbers. However, they're kind of, at least for toric varieties, I'm not sure that they feels to me like fake rational numbers. So if you have time in this course, we will talk about it. And by fake rational numbers, I mean that that kind of, if you look at correlation functions in Landau-Ginzburg side of theory, you still get integer numbers even in descendant case. And that kind of rationality comes from some extra transformation between descendants on A side and descendants on a B side. So that's why, in a sense, you have like a very controlled rationality of these numbers. I'm not sure like how standard this result is. So in the literature, it was an observation made by de Young in his paper with Dubrovin, where they kind of explicitly studied like Gromov-Fit invariants of P1, and they noticed that in genus 0, the denominators for Gromov-Fit invariants of descendants, they have like a very small number of prime factors. So it's essentially like very large denominator, but they are essentially like large powers of a small number of prime factors. And then kind of, it turned out the explanation for this fact was very easy, that these prime factors, they were just encoded in some mirror map between descendants from A side to B side. So that's why, yes, they are rational numbers, but kind of the denominators are easily controllable, at least in kind of toric cases. But hopefully we will get to that topic sometime later in the course when we will talk about descendant invariants. So for now, it's just a remark that that this kind of integer coefficients is a special statement of genus 0 and kind of no gravitational descendant here. Tau 0, so no gravitation. Okay, so let's go back to our simplest example. So here H star of P1 is kind of generated by two generators, so it's kind of like gamma naught, which is just constant form, so we can choose representative which is identity everywhere, and kind of two form for which we can have different representatives. So sometimes people use Fubini-Studi form, so that is kind of smooth representative with which is like supported everywhere, or you can use something more singular, like Poincare dual for a certain point. So that is kind of singular to form. So Poincare dual to a point kind of gives you immediate geometric interpretation for these numbers, while kind of for if you want to study integrals, then you might prefer to work with a smooth representation. Here we actually like computed all Gromov-Witten invariants for P1. I think it was like lecture before the last lecture, so let me kind of give a brief summary. So for 3-point functions, we have only two non-vanishing 3-point functions. So this one, when we have gamma naught, and gamma p, so that is just a classical intersection, and this is just one. And if I have gamma t, and gamma p, that is Q. So it's kind of some intersection of a degree 1 curve. And the only other non-vanishing invariants, they are invariants when you have like arbitrary number of this insertion of gamma t, and they're still equal to Q, and we've proven this using kind of divisor relation. And okay, so for the sake of illustration, so if I have gamma naught and say kind of gamma 1, gamma n, so that is vanishing given that n, at least in our formulation, is real high. So that is kind of essentially all Gromov-Witten invariants for P1. So if you insert gamma 0 and you have 4 or more total observables with gamma 0, so then this thing vanishes. And for 3 observables, including gamma 0, there is kind of one non-vanishing case when it's gamma 0, and gamma p. And you can insert arbitrary number of gamma p, like 3 or more, and still get the same answer. So that was kind of full story of Gromov-Witten theory in P1. So our first step today would be to kind of adopt a definition of these correlation functions that I gave at the end of last lecture, and compute all these Gromov-Witten invariants for P1 to kind of for this mirror Landau-Ginzburg-Saito theory, and kind of explicitly verify that this mirror relation kind of works, that this we have like full list of Gromov-Witten invariants, and we can reproduce all of them using recursive procedure that was given last time. So then we will discuss like some other aspects of kind of one-dimensional version of Landau-Ginzburg theory, and only after that we will go to higher dimensional version and discuss some additional kind of problems and features of higher dimensional Landau-Ginzburg. Okay, so let's start with the second line. So let us look at Jacobi ring for CP1, for mirror of CP1. So we have like holomorphic functions, and we moved it by gradient ideal. So our holomorphic functions, they are essentially like some kind of, we can say it's polynomial of e to the iy and e to the minus iy. So any polynomial of these variables is a holomorphic function in this y coordinates. And then we kind of quotient by gradient ideal, and gradient ideal is generated by just w prime. So we quotient by relation e to the iy minus q e to the minus iy. So this relation essentially allows us to eliminate all powers of e to the iy. So except kind of zeroth power and our choice of some other power. So let me just for the sake of saving some notations, let me use kind of secret correct answer. Q e to the minus iy, but at this point you can choose like any other power. So that still would be okay on the level of Jacobian. And for notational reasons, let me call this object phi 0 and this object phi t to kind of have analogy with two generators of cohomology like gamma 0, which is constant form, and kind of Poincare dual to the point on CP1 gamma. Okay, so that is our mirror for observables. So now let us start with the 3-point function. So we have like this 3-point functions on this non-vanishing 3-point function on CP1. So let us recall from our formula if you have like 3 5s. Sorry. To avoid using numbers, let me call it gamma I to indicate that it's kind of identity, because I often will use like gamma A's to indicate like gamma 1, gamma 2, and gamma 3. So to avoid kind of some misconception, so let me label gamma I and gamma P like letter subscripts versus number subscripts. So number subscripts mean that they can take any letter value. So essentially the phi 1 is kind of belong to set. So we take like this three holomorphic functions, and then kind of our first part of the definition for endpoint correlation function was if you have 3-point function, then we need to take, okay, in general, multidimensional residue. In our one-dimensional case, just one-dimensional residue. Okay, and because this mirror superpotential has isolated critical points, we can as well rewrite this residue as the sum of the critical points of W. And here we do the following: we evaluate the product of 3 functions in a point P and divide by kind of W double prime evaluated point. So we have 2 critical points, and this sum has 2 terms. Okay, so now what we can do? So let me start with this kind of example. So let us choose. Yeah, let us first verify that we get like this identity. So let us choose phi I, p. So here we sum our critical points, and phi 1 and phi 2 just 1 times 1, and phi p is just q to the minus iy. So what are the critical points? So critical points for W. So they are fair, so like y plus minus, such that e to the iy plus minus equal to equal to q. So okay, let me do it. E to the I y plus minus is plus minus square root of q. So and W double prime is what? So we need to take second derivative of this thing. So that will be minus e to the iy, and here minus q e to the minus iy And if I calculate W double prime at these two critical points, y plus minus, then what I will get minus plus 2 square root of q. So it will be like minus square root of q, like for y plus, it's minus square root of q here. And if I substitute, I will get another minus square root of q from the second term. So it's minus plus 2 square root of q. So therefore here, for summation, we can say summation over plus minus. And evaluation of p at y plus minus. So at y plus, we need to divide q by square root of q. So we give a square root of q, and the sign plus minus. Therefore here, I can just say plus minus square root of q, and here minus plus. Okay, so up to overall sign that I unfortunately messed up. Okay, so let me add a sign. I messed up with the sign somewhere. So okay, so if I put an overall sign, so then what I will get, so square root of u cancel, and we get like, and plus minus cancel, so we have like summation over two values of a constant function 1/2. So that gives us 1, and which indeed matches with the answer that we had in Gromov-Fitting theory and so on. So in a similar way, like let's say we try to compute something like phi I, phi p. So it is Gromov-Fitting invariant that vanishes on Z1. So and similarly here, okay, there is minus sign, so there will be summation over this plus minus, and now we have 1, and we have like 2 copies of phi p. It will be plus minus square root of q, but now it will be squared and divided by the same denominator. And now not all signs cancel, so we will have like 1/2 summation, and here will be plus minus square root of q, and this thing, because we kind of add plus square root of q and minus square root of q, we get answer here. So in this case, we kind of see this property that naively you would think by substituting like powers of q that we may run into trouble that the answer is not polynomial in q, because in numerator we have like square root of q squared, and in the denominator we just have square root of q. But it turns out that each time we have square root of q, it kind of comes with this alternative signs. So therefore, in order to get like non-zero answer, we need to cancel all alternative signs. And canceling all alternative signs means that we have like sort of odd number of square root of q in the numerator divided by square root of q gives us even number of square root of q's, and that gives an integer answer. So, and I think there is some general formula that we might need later. So if I have something like this, so the product of these functions will always be like some kind of exponent of this type, like some kind of e to the I and y, where n is some integer number. So let us kind of calculate this expression like for a generic exponent divided by w double prime. So here e to the I and y will be plus minus square root of q to the power n minus sign. And here will be 2 minus plus square root of q. And the answer will be the following. So anytime that n is odd, sorry, anytime that n is integer, so the answer is 0 if n is integer, because we have like summation over the same expression with alternating signs. And in a case when n is odd, so n is k plus 1, k is integer. So then the answer will be just q to the power k. So that's why we kind of indeed see that answer is either 0 polynomial, regardless of what kind of monomials we have in the numerator. So if you evaluate in kind of monomials in this e to the iy variables, then we always have integer. Okay, and kind of similarly, you can verify that this 3-point function, which is kind of the 3-point function responsible for kind of quantum multiplication because it's equal to q. So if you have phi p, and another quantum phi p, so that is kind of our special case when kind of n equals -1. So n equals -3 because we have like a product of 3 e to the minus I and y. So -3 means it's -2 times 2 times -2 plus 1. And we also have another power of q. So it will be like q cubed. This one is like q times e to the minus iy. So it's q cubed from these three factors of q and another factor q to the -2 from the general formula. That just gives us q. And so indeed, we kind of verified that 3-point functions, they indeed match with 3-point functions computed in Landau-Ginzburg set. But that's kind of hardly surprising because here we sort of using some standard properties of Jacobi ring, like in addition to some kind of residue pairing that we added to Jacobi ring to kind of turn structure constants into kind of 3-point functions. So that is kind of hardly surprising. So let me make one kind of remark that will be important later. So if you look at kind of definition for a 3-point function given by this way, so we can definition for a 3-point function. So from is the following property. So if I take phi1 and shift it, so remember here, yeah, I think color is a different color. So here we kind of define this classes in this Jacobi ring as kind of some set of functions up to shift e by gradient again. So here, like if we try to shift, like say, first observable by elements of a gradient ideal, which is in one-dimensional case, like all vector fields are just one-dimensional. So, but still, let me kind of try to write it as a vector field, like v times w prime, and keep phi2 and phi3 the same. So then, by the nature of residue formula, so here what we will have, like phi2, phi3 times v. And then denominator would cancel. So in denominator we have w prime, and we have another copy of w prime in. Okay, let me do it the following way. So this expression is kind of linear in 3 arguments. So let me kind of consider a difference between this and I subtract like original one. So the difference will be proportional to kind of difference in phi 1 and phi 1 plus VW prime. And here notice that W prime will just cancel, and therefore there are no poles because no denominator. So this residue vanishes. And similarly, in the sum of the critical points, like every time we have V times W prime, so that W prime vanishes the critical point. So we literally multiply like any term in the sum by 0 because the term is proportional to W prime. So therefore, from this observation, we make a kind of conclusion that 3-point functions, even though we define them on the functions, because we need explicit functions to evaluate them at some critical point. So 3-point functions in LGS theory, so they actually descend to kind of classes in Jacobian. So we can as well say that given this definition in holomorphic functions, since the answer is independent on the shift inside the class, so we can as well say that 3-point functions are defined in class. And that is once again hardly surprising because like these 3-point functions, they are responsible for kind of quantum cohomology structure on kind of X. So quantum cohomology as a ring, kind of the model to Jacobi ring, and here we use sort of residue formula essentially as a way to rewrite the multiplication structure in this kind of Jacobi ring. So that's why it's hardly surprising. However, the second part of the remark, which we will see a bit later, so I will return to it. So this property does not hold for higher point functions. So not true. So this property not true for bigger than. So for and higher point functions, they actually would depend on which representatives we take in this like classes in Jacobi ring, and we need to get this mirror relation. So we need to choose like very special representatives phi a, and these special representatives they will be from this specific image of a good section. So good section will give us a very specific choice of holomorphic functions representing each of the classes in Jacobi rings. So that is kind of somewhat different on left-hand side, because on left-hand side it's still this Gromov-Fit invariants, they are still defined on classes, so you don't need to use specific differential forms to compute them. While on the right-hand side, kind of you need to use specific function, and we will see, I think, in some time, like why this is not true, and what is the difference if we try to perform this procedure for say 4-point function. But before we kind of check the second remark, so we need to get familiar ourselves with 4-point function computation. So I need to erase something.
So what happened in this case? The n-point function left hand side is just q, but in right.
Yeah. So we are now will be computing. So we will. So today we will get like all n-point functions computed in kind of mirror Landau Ginzburg side of theory 41. So that kind of was main reason why I wanted to kind of split our discussion of Landau Ginzburg side of theory into one-dimensional case and higher dimensional. So let us kind of, as a first step to n-point functions, let us look at the 4-point function. So So for 4-point functions, so let me start with this first simple 4-point function. So let me kind of take 3 observables time of a type phi p and 1 observable of a type phi I. Okay, so what you do here, we want to do kind of Landau-Ginzburg-Saito recursion. So that is our definition. And for recursion, we need to kind of choose one of the 4 observables and perform recursion with respect to it. And let us first kind of choose this phi I as a kind of variable or as an observable which we will use for our recursion. So that's why recursion in this setting will give us, okay, 4 terms, but 3 of them will be of the same type. So I will just write it to the factor of 6. So the first term is the derivative term. So we take phi p, phi p, phi p, evaluate it, and kind of deform it superposition. So we deform it by epsilon times phi I. And then there will be 3 more terms. Okay, so here let us also notice that kind of 3-point function is symmetric in 3 arguments. So here, like, it's symmetric for obvious reasons because the answer depends only on the product of phi 1, phi 2, and phi 3. So that's why here, when I have kind of, let me first write like a full formula and then abbreviated version. So then in recursion, we need to kind of add up 3 more contact terms between this kind of each of the observable and the observable phi I that we use to run recursion. Let me kind of draw it in different colors to kind of give some indication what depends on phi I, like to highlight dependence on phi I. So it's W phi P, again phi I, phi P, and computed transforming theory, and the very last term okay, and once again computed transforming. So then here, kind of using symmetry, so second line, essentially simplifies using symmetry. That is just 3 copy of, let's say, first expression. So then we use our definition of a contact term. So let us, maybe I can do it in the following way to keep all formulas. Let me kind of on this board keep a definition of a 3-point function and supplement it with kind of formula for contact term, and I will keep it on board to return later. So the general construction was the following. So given pair of functions, say phi 1 and phi 2, so this pair of functions is not necessary from image of a good section, so that's why I draw them as kind of capital phi's versus calligraphic phi's for good. So for this pair of functions, we define a kind of another function, phi 1, phi 2. So that is also a function of C star in our model. Of C star to the power n, and the rule was the following. So first, we take a product of these 2 functions. It's also product of homomorphic functions is also some formula. So then we do the following thing. So for a product of homomorphic functions, we can evaluate kind of its class in Jacobi ring. So pi w is just a projection from homomorphic functions to kind of classes in Jacobi ring. So function f get mapped to class of f, which we can just sometimes denote as PW of f. So I think it's kind of better to use PW of f to kind of keep track of W dependent. Okay, so then this thing is an element in Jacobi. So then we use our additional data, which is the section that is a map from classes in Jacobi ring to some holomorphic functions that are given by this formula. So we apply this section map to a class and get a holomorphic function. So therefore here we apply SW. So now we kind of constructed some holomorphic function. So we first projected the product of holomorphic functions, get a class of this product, and then used a very specific section to give us back a holomorphic function. So then we construct this difference, and for this difference we have the following property. So if I apply, say, projection to this difference, so then by construction, what I will get that it's EW of a product. But then by definition of a section, so composition and by W composition with SW is just identity in Jacobi ring. So that is definition of a section. So therefore here, like pi w composed with SW will give just identity in Jacobi ring. So that's why we will have another copy of pi w applied to a product. And therefore this expression is 0. And this 0, like to be more precise, is kind of 0 class in Jacobi ring. So because here we computed like pi w this expression, so it's some element of Jacobi ring. So 0 class in Jacobi ring means that that it represented by kind of functions that are elements of the gradient ideal. So it's kind of functions that of this form. It's like some vector field acting on holomorphic vector field acting on our superpotential W, or kind of in components it's Vk times partial derivative k of W. So then what we said that now for this white expression, because it kind of white expression is kind of projects to a 0 class in Jacobi ring, means that it is itself element of gradient ideal. So it means that there is the kind of vector field such that this expression is Vk dk dash. And then what we said that by definition, contact term between this pair of functions, that is our definition, is the following object. So we take kind of holomorphic divergence of this vector field Vk. So let me kind of give it a label V12 to kind of keep track that this vector field constructed from pair function. So that is color in yellow. So that is kind of our definition for a contact term. So we take a pair of functions, multiply them, subtract kind of good section applied to kind of class of a product, which is product of classes. Get by this subtraction we get a kind of element from a trivial class, which means that it is element of gradient ideal, and then we take kind of coefficients of this element in kind of basis of our gradient ideal basis given by partial derivatives of W. And then we kind of apply holomorphic divergence to this vector field, or in kind of coordinates where holomorphic form is just product of dy1 to dyn. So this holomorphic divergence is just kind of summation over yk derivatives of vt. So that was our construction for good section. And once again, this construction is kind of simplified if we go to kind of one-dimensional case. So when kind of our superpotential only depends on a single variable. So in this situation, we can immediately solve for V12, because now it's kind of not some sum of a k equals to this expression, but only one term in a sum. So this one is just 1 phi 2 minus w by w 1 phi 2. And here all we need to do to divide by w. And then kind of also this holomorphic divergence also simplifies a lot because we have only one component. And kind of here, as you see, this contact term, it only depends on the product. So that's why, for the sake of having like less notations, I will often like drop this comma because it depends on the product anyway. So CW phi 1 phi 2 is, we can write this kind of formula by 1 phi 2 divided by W prime, and here another. So that is kind of our formula, right? That is a kind of contact term in one-dimensional plane. Okay, so now after we simplified contact term in one-dimensional setting, let us kind of compute some contact terms in our mirror theory for P1. So let us kind of compute this phi p, contact term between phi p and phi I. So by definition, what we need to do, we need to kind of calculate some difference divided by W prime and then take a derivative. So phi p. So here I can use my explicit form for phi I. So phi I is just identity. So therefore phi p times phi I is the same as phi p. And here we kind of subtract section applied to projection of this function. And here what we have. So projection of phi p will give us class of phi p. But then we use this property that kind of image of this section is again phi p. So therefore here, like by construction, as W of a class of phi p is phi p. So that is our choice of SW. So therefore here we have like phi p minus phi p divided by W prime, right? So phi p minus phi p is 0, so 0 is kind of nicely divisible by W prime. The answer is 0, so 0 prime, which is again 0. So here, like this contact term, they just vanish, and a 3-point function is kind of linear in all arguments. So if you put like 0 times some phi, so then the answer would be 0 times some 3-point function, and that will also give us 0. So because we have like one argument 0, so then this whole correlation function also vanishes. Okay, so that is good. So we use our kind of good section, explicit computation for contact term to basically compute like all these three contributions. Okay, so they are all equal to each other and equal to 0. So therefore, for a full-point function, we only left with a single contribution, which is 3-point function of phi p, and phi p in a theory with deformed superpotential. Okay, so I still want to keep that word, so let me erase that one. Okay, so once again, we use our definition. So and in our definition, 3-point function of phi p in the formal theory. So what? So we need to take a sum over critical points of the formal superpotential, and here evaluate like phi p divided by w deformed w double prime, and kind of evaluate for at each critical point. Okay. Yeah. Okay, let me call it R because I have like capital a little bit, so just to avoid confusion, let me call critical point R. So now let us notice that our kind of equation for critical points. So critical points are solution to the following thing. So my I prime evaluating the critical point should be 0. Y labeled by R should be 0. And let us notice that since phi I is just identity, so essentially what we do, we take our original superpotential and just add epsilon times 1. So we just add a constant term. So adding a constant term means that if I take derivative with respect to y, like compute w prime, so then this derivative will just eliminate this constant term. So therefore w prime is kind of insensitive or independent on this epsilon, and therefore the critical points for w and critical points for w plus constant are the same critical points, and kind of the same holds for second derivative. So first derivative is independent on epsilon, so the second derivative is also independent. So therefore this expression is epsilon independent. And if it's epsilon independent, then taking derivative with respect to epsilon will just turn it into 0. Vanishes because this expression is the expression to which we apply epsilon derivative is epsilon. Okay. And kind of before the break, let me kind of end this part with kind of natural question. Like here we choose phi I to perform our kind of recursion. However, since we haven't proven that the kind of Landau-Ginzburg-Saito correlation functions after like recursion procedure kind of breaks immediate symmetry in all arguments for Landau-Ginzburg-Saito correlation function. So therefore, you may naturally wonder, like, what would happen if instead of using phi I as kind of observable to deform our theory and apply recursion, what if we use phi p? So would the answer be the same or maybe different? and we will like repeat this computation for the case when we perform recursion to the same correlation function, but we will compute it in a different way by performing phi recursion. And that we'll do after the break. So let us make a 7-minute break, and we will return at 11 off. So I want to end this with some kind of cliffhanger.
Or maybe we have get a puncture relation for Delgy theory.
Yeah. So we will do this in next part. That indeed we can kind of generalize this simple computation into puncture relation. Yeah, maybe that's a good point. So before I arrange this computation, we will first generalize it to a puncture relation and then kind of compute the same correlation function in kind of using recursion with respect to different arguments.
Oh, the common term is not unique. So
No. So that's kind of the key simplification, one-dimensional case. That in one-dimensional case, the contact term is unique. So because here, like there is kind of explicit formula for it. So there is no non-unique. So the non-uniqueness came when you have kind of more than one variable, because then here you have like some vector field which can have two components, and you can imagine that there might be some vector field V that is kind of symmetry of double. So V that acts trivially on our superpotential double. So then I can freely add, if I found one V, then I can add like a symmetry with any coefficient, like any holomorphic function as a coefficient. So that's why, and but for this thing, we need to be in dimension kind of with two or more variables, or in dimension 2 and higher. And that's kind of a main reason why I wanted to first talk about one-dimensional Dahl-Ginzburg side of theory when the things are kind of easily defined. That recursion procedure doesn't require like further clarification and justification for its existence. But hopefully, like at the part 3 of today's lecture, we will like go back to this issue of non-uniqueness of contact terms and why non-uniqueness of a contact term doesn't prevent us from running this Landau-Ginzburg side recursion. So the contact term will be indeed non-unique, but the answer for recursion procedure will be insensitive to this non-uniqueness. So that's why we will need to kind of identify what is the general structure of this non-uniqueness and then show that there is some redundancy in this endpoint functions, and this redundancy is just enough to accommodate for non-uniqueness of contact terms. Okay, so Yeah. Let me also erase that part. I think we are kind of got familiar with this Landau Ginzburg site data for CP1, and I think the probability invariants are also very simple, and we talked about them multiple times, so I don't need the formulas on the board. Okay, so let me start with this kind of observation. So observation of the following type, that in our kind of logic for, or in our derivation for proving that phi p vanishes, so we can actually do several generalizations. So first of all, we can freely replace like all kind of three other arguments except phi I. We can freely replace them by arbitrary kind of arbitrary element of a good section, and this argument still runs through because element of a good section multiplied by 1, so projection and kind of section applied to it will still be equal to phi I multiplied by identity. So therefore in this case, as long as this phi a's belongs to kind of image of FW, so we still have, so that kind of implies that the constant term between phi A and phi I will still be 0. Okay, so that is, and similarly, the argument about 3-point function is kind of even, about derivative of 3-point function, which I raised, is even more robust because it doesn't matter like what superpotential we have as long as we shift it by a constant. So W, so kind of 3-point functions of arbitrary phi 1, phi 2, and phi 3, they are always equal to 3-point functions evaluated as W shifted by constant. Because in the 3-point function, the dependence on W is through some at least first derivative of W. So therefore, these two arguments they kind of generalize to arbitrary elements here, and furthermore, using this general formula for a good section, like if for a moment we ignore this issue with non-uniqueness of V, we see that there exists at least one V that is V equal to 0, because by kind of the same logic, if I take phi 1 from image of a good section and phi 2 is just identity, then this difference is not only represent trivial class, but gives you like trivial function representing trivial class. So therefore I can choose V equal to 0, and that is one of the choices, and that once again leads to a vanishing contact term. And therefore kind of observation that this construction can be generalized to any LGS theory. And that gives us that phi I, phi 1, phi 2, phi 3 is 0, and then invoking kind of recursion, you can further argue that can be further generalized to kind of higher point function.
Why it being 0?
Why
it equals 0?
because we don't have descendants. Like in a puncture relation, the right hand side is kind of only non-zero if you have descendant invariance.
You mean the first term?
Yeah, the first term is zero because the 3-point function is insensitive to shift of a w by a constant. So that's why derivative term always vanishes. And once again, for a moment, ignoring non-uniqueness, like we can choose a v12 which is just equal to zero, and that will give us zero contact term even in higher dimensional case. So therefore, using this kind of zero contact term and kind of observing that 3-point function is independent on epsilon, so that gives us a kind of general proof that this 4-point function in any Landau-Ginzburg-Side theory, as long as this phi1, phi2, and phi3 belong to image of a good section. So then this thing vanishes. So let me, yeah, I think that maybe kind of a good point to illustrate the importance of this property before we will go to higher point function. So let us kind of redo this computation if we choose this phi not from a good section. So they are still kind of, so this recursive procedure is in principle defined on any other functions. So let me choose here, like choose the function e to the 2iy. So that is not an image of a good section, because image of a good section, so that is kind of, we choose image of a good section to be kind of linear span of phi I and phi p. And this thing 2 to the iy is not a linear span of phi I and phi p, so it is kind of belong to the same class as phi I. So kind of class of e to the 2iy. Let me even put just q to the power. Okay. So class of this thing to the q times kind of class of identity. But this thing e to the 2iy as a holomorphic function is not the same as 2 times identity. So they differ by element from a gradient ID. So now let us try to, and here let me still use phi p for simplicity. So let us try to compute this 4-point function. So this thing is still identity, these are still phi p, and here instead of using kind of element of image of a good section, we use some arbitrary holomorphic function. So now the argument about 3-point functions is still valid, regardless whether we have a good section or we have something else. So we still take some kind of one-dimensional, high-dimensional residue with a superpotential shifted by constant. So this term kind of vanishes. So this argument about so this still vanishes. So then we have 2 terms where we have a contact term between phi I and phi p. So between phi I and some element of the good function, phi e to the 2iy w. So this term is still vanishes because this contact term vanishes. We computed it before. However, we have very last term, which is contact term between phi I and into the iy, and here 2 phi p itself. So now let us compute this contact term. So by definition, w into the 2iy I. So what we need to do, we need to multiply them. That gives us e to the 2iy. Then we need to subtract kind of good section of a class. So we already computed class of the e to the iy. It's a q times class of the identity, and kind of the section map is linear. For here, it will be q times identity. And now this difference is not zero. So now we need to kind of write down w prime in denominator. E to the iy minus iq e to the minus iy, and take prime. Okay, so once again, kind of general formula tells us that this thing should be divisible, divisible in kind of ring of polynomials in e to the iy and e to the minus iy. So no kind of infinite series. And indeed, we can see that if we multiply denominator by what? If we multiply denominator by minus I e to the iy, so then we will get exactly a numerator. So minus I e to the iy will give us e to the 2iy from this term, and from this term we will get like minus I times minus 1, and that will be q times and here by dependent term. So that's why we multiply the numerator and denominator by this expression. So then multiplication of this expression by w prime will kind of exactly cancel the numerator. So these two terms will exactly cancel, and what we left is the derivative of minus I e to the iy, and that is easy, and that gives us just e to the iy. Okay, let me kind of finish argument here, and then we will get into generalization. So okay, maybe I can rewrite something. Okay, so let me erase that part because it is zero anyway, and kind of this part is zero, and let me somehow continue on the same side. So that is kind of 3-point function that we want to compute. So we explicitly computed contact term, and it gives us the iy as the first argument, phi p evaluated at w. Okay, so now this 3-point function is kind of okay. So it's not immediately zero. Like it's not a 3-point function with one argument is 0 times some function. So okay, so we have our general formula, which I erased, like a 3-point function where we have like a product of these 3 components is e to the I something, but let us explicitly write it. So sum over critical points, which is like plus minus in this situation, and what we have in the numerator is e to the iy from a first argument and q e to the minus iy twice from second and third argument, and divided by w. Okay, maybe I can like do it even simpler. So let us notice that e to the iy, the kind of the class in Jacobi ring of this thing, is actually the same as the class of q to the minus iy, because w prime is precisely a difference of these two terms. So therefore, difference of these two functions is w prime times I. So they are the same class, and we kind of have this remark that I raised, the 3-point function descends to the classes. So that is kind of class of phi p, and due to kind of 3-point function depending on classes, So we can freely replace this representative by another representative from the same class. So let us replace just phi p by phi p, because phi p kind of belongs to the same class. And we get 3-point function of phi p, phi p, phi p, which we computed earlier, and that equals to q. And therefore we arrived into kind of an interesting observation that if I kind of forget about this additional assumption that I substitute only kind of elements from a good section into 4-point function. So instead of element from a good section, I kind of put some other function from the same class. So here, instead of using from the same class, like so here I substitute this thing, which is a function from a class of identity in Jacobi ring. And instead of using identity representative as kind of dictated by image of holomorphic section, I use some other representative but from the same class, and perform Landau-Ginzburg-Saito recursion, and I arrive into non-zero answer. So the answer for this 4-point function is q. And that kind of illustration of importance of this condition, that kind of this 4-point function with kind of identity insertion vanishes only if other 3 observables are from image of a good section. And if I am not from image of a good section, then this thing is generally non-vanishing. So that is kind of an important illustration of what I said at the beginning of my lecture, that that left-hand side, like Gromov-Tate invariance, is defined on cohomology classes. You can choose any representatives for your cohomology classes. While on the right-hand side, you need to choose a specific holomorphic functions to insert them into this Landau-Ginzburg-Saito correlators and run Landau-Ginzburg-Saito recursion.
So is there something correspondence with exponential 2i in the case?
Yes, so indeed, and if we will get to that kind of, so we will get to that hopefully later in the course, but this thing is in a proper sense equivalent to the following expression. So it is kind of q plus sort of first descendant of okay, now let me recall. I think it's first descendant of phi p. And this correlation function is secretly a sum of 2 terms. Like one term is this vanishing correlation function, like vanishing 4-point function, like vanishing Gromov-Tate invariant with just identity kind of cohomology insertion, plus some kind of Gromov-Tate invariant that involves like level 1 gravitational descent. And in a 4-point function, if I include gravitational descendants, then as you're probably familiar, if I apply kind of puncture relation, there will be indeed right-hand side where I kind of will decrease the descendants level of one of the observables by 1. And this thing, like this phi I will eat up one level of gravitational observable, and indeed will give us precisely a 3-point function of that. So therefore, indeed, kind of choosing different representatives from the same class is kind of shifting our correlation function by kind of additional terms that include gravitational descent.
So the whole story, the LG theorem, can correspondence.
Yeah. So indeed, there is a kind of, at least for CP1, I kind of proven that this mirror relation kind of could include gravitational descent. But I need to do some modifications to Landau-Ginzburg-Saito theory to kind of properly define the correlation functions in the presence of descent. But indeed, it is true that this relation kind of extends to gravitational descent. And I think that is something that people haven't done, like using topological string or using some kind of QFT methods in the physics literature. Because for QFT methods, like accessing this tau1 is kind of extremely complicated. While it is still possible using kind of tropical version and tropical mirror. But that is kind of more advanced content which I want to kind of avoid to discuss right now, and we will return to it in kind of later part of the course. So that was kind of some remarks. So for now, it was just an illustration of importance of this rare condition. Okay, so now, so I can generalize this argument to any 4-point function in any Landau-Ginzburg space, and then kind of using Landau-Ginzburg recursion. We can actually prove by recursion in kind of number of arguments. That indeed stronger version holds that if I take an arbitrary number of kind of observables that are holomorphic functions from image input section, that this thing is vanished. And that relation, I think, is some kind of version or Landau-Ginzburg-Saeta puncture relation. And that is kind of mirror of a very simple property of Gromov invariance, which is also puncture relation, that if you look at genus 0 Gromov invariance without gravitational descendants, then you have the same property that for and the higher point functions that contain this identity in the sense of differential forms observable, this kind of Gromov invariant vanishes. Okay, so that is kind of a good sign that we not only get like a matching of some subset of Gromov invariants to Landau-Ginzburg-Saeta correlation function, but now we have like a matching of the whole family of invariants that contain insertion of at least one kind of constant observable on either side. So both sides, they kind of have matching correlation functions because both of them equal to 0 due to kind of mapping of puncture relation from Gromov-Itten theory to Landau-Ginzburg-Saeta. So in a sense, in the CP1 case, that leaves us with only other family of correlation functions when we have arbitrary number of phi p insertion. But before going to this family, I need to kind of answer this teaser that I did for the break. So to kind of see what would happen if I try to run LGS recursion using, say, phi p as kind of my deformation for a thing. So yeah, let's do it on this board. We will do some partial computation on this board, but mostly let us get the corrections. So we kind of eliminate this thing. So now we treat these three observables as the fixed observables, and this one is a deformational theory. So we kind of eliminate this answer, and here we use yellow and write phi p, and here it will be phi I, phi p in this deformed theory where we deform W by epsilon phi p. So now, okay, let me that part. Okay, so now let me erase all this in green. We have different frequent functions. Okay, so now we have the following three contributions. So there will be okay, phi I, phi p contribution. So then there will be phi p contribution. And the very last term, it will still be phi p contribution. And carefully replace it. Okay, so I kind of redid the Landau Ginzburg side recursion using now this phi p variable as my deformation for a theory and kind of deformation for observers. Okay, so now we already computed the contact term phi I and phi p, and it is 0. So therefore, we can eliminate one term in among three. So this term vanishes because we have a familiar vanishing contact term. Okay, so now in these other two terms, other 3-point functions, we have different contact terms. So now we have contact terms CW of phi p and phi p. And we need to compute it. And here what we have, we need to multiply phi p by phi p. So phi p times phi p is q squared e to the minus 2iy. So what is a class of this product in Jacobi ring? So the class of this product is actually okay. So when a class is the kind of ring structure is that if we multiply two phi p's, then we get like something proportional to phi I. So therefore it will be like something proportional to phi I. And then here we can restore this constant that it should be q proportional to phi I, because in a sense like all objects have some q grading. So q plus of phi I. So therefore here, if we apply kind of good section to this thing, it will be q times phi I. So the kind of good section applied to kind of class of a constant is a constant itself. So therefore here we have the following formula. So we have q squared e to the minus 2iy minus q times 1. And once again, the numerator is non-zero, so we need to kind of honestly divide by w prime and take a derivative. So let me even write explicitly w prime is I e to the iy minus e to the minus I. Okay, and once again here we can kind of perform this division by multiplying a numerator and denominator by some factor. So if in order to get a numerator, we need to multiply the denominator by the following factor. So we want to multiply it by q e to the minus iy to get something similar to this term, and we need an extra minus sign to cancel minus sign here. So if I multiply my denominator by this factor, I will get q squared e to the minus 2iy, the same as the first term. And for a second term, sorry, I missed factor of my iq. So that's why here I need to multiply it by iq e to the minus iy. So that's why this I times minus I will give me a plus sign. So then multiplication by this factor of a first term will give me exactly minus q. So therefore kind of, if I multiply a numerator and denominator by this term, I will get kind of cancellation between original numerator and modified denominator. So therefore, this ratio is equal to this term. So we need to take a derivative, and derivative will give us q e to the minus iy, which is the same as this image of a good section applied to this kind of non-trivial class in Jacobi. So therefore, we have this very nice formula that the contact term between phi p and phi p is just phi p itself. Okay, great. So therefore, now we can compute. We can simplify these two terms. And what we left? We left with the following 3-point function. So it's phi I. Then for the contact term we have phi p, and we have another phi p, and we need to compute this 3-point function. And this 3-point function, it kind of vanishes because it is kind of proportional to kind of even power here, q e to the minus iy squared, and that is this kind of even power in numerator, odd power in denominator. So therefore, summation of a plus minus would give us zero. So therefore, this pair of 3-point functions, they are not kind of immediately vanish because contact term vanish, but they vanish because 3-point function computed with their contact terms, they vanish. Okay, good. So 3, we kind of managed to eliminate 3 terms out of 4. So now we need to look at this term, and so here this term is not immediately vanished because we shift superpotential W to W plus epsilon phi p, which is in our notation is like e to the iy plus q e to the minus i1 plus epsilon times q e to the minus iy. So that also looks like a superpotential. So we can just say that if we kind of keep track of a q dependence on the superpotential like parameters, so then kind of deformed superpotential will be a superpotential with the scale q by 1 plus epsilon. So deformed by epsilon phi p is kind of the same. So it's like a scaling q. So we can call this mu q epsilon. So it's a superpotential of the same shape, but deformed parameter. Like parameter is rescaled by 1 plus epsilon. So which is good because then we can do the following things. So phi I, phi p, phi t. And here we just have W with deformed Q. So W of the same shape. So same shape means that there is kind of same condition for vanishing of a 3-point function. So, and we already checked that that this 3-point function in kind of W of Q vanishes. And since we don't care about Q dependence, only care about shape of W, so then this object is also vanishing, and therefore this derivative is vanishing by the virtue of 3-point function itself vanishing. So it means that derivative of 0 is also 0. Okay, so therefore now we kind of verified on one example that even though Landau-Ginzburg-Site recursion looks very non-symmetric in arguments.
Excuse me, here we deform this W.
Yes.
By adding E epsilon phi p.
Yes.
Then, should we change the cycle section to?
No, okay. So the section will
The Jacobi ring will change. Oh,
the Jacobi
Jacobi
ring
ring
will kind of deform. So it will still be two-dimensional Jacobi ring, but kind of classes would slightly deform because the multiplication is dependent on this QX. So previously, like if I multiply class phi p by class phi p, I get like q times class of phi I. And now in deformed Jacobi ring, I get like same shape of multiplication but with a different parameter QX. So in this sense,
I mean, if we define this 3-point function as a integral, as a
but
residual integral, then shall we change the numerator?
You need to change the numerator, but here it kind of vanishes for even simpler reason, for some kind of degree selection rule. But if we want to compute, and we will compute in a moment, say something like this. So in undeformed theory, we saw that this 3-point function is Q. So now what about if I compute the same thing in a deformed theory? So if I deform W by Q epsilon. So then I will have Q epsilon dependence. And there are like two ways of kind of computing this. So one way is to just use a definition and kind of notice that there will be like Q cube from these functions, and then there will be something like Q epsilon to the power minus 3/2 from evaluating e to the minus iy at the critical points, which now will be determined by W that depends on Q epsilon. And then there will be another factor of Q epsilon to the power 1/2 in denominator is kind of W double prime evaluated at deformed critical point. So that will give us the following dependence. So that will be what? So that will be okay. Now I'm okay, good. So it will be Q cube divided by Q epsilon squared. So that is kind of 3-point function, and that can be simplified if you use explicit form of Q epsilon. That will be Q 1 plus epsilon to the power minus 2. So indeed, like 3-point function that were non-vanishing in original theory, if I change the parameter in a superpotential, so they will change in a rather non-trivial way. So alternative way of computing this 3-point function.
So the first factor q to the power 3 means we still use the same section.
Yes. So this might be, yes, they evaluated that q. So that was the rule that we keep observables the same and only deform doubly. So that, sorry. So that was the rule in our Landau-Ginzburg-Saito recursion, that there are two types of terms. So we either deform observables by contact terms, or we keep observables literally the same as a function, the same as homomorphic function, and deform W by one of the observables. So that's why here this Q dependence of phi p doesn't get deformed by epsilon. And that kind of gives us an alternative way of computing this expression. So if instead I kind of pretend that I deformed phi p by substitute like epsilon in my definition of good science. So emulate this thing at QX. So then this answer is easy to evaluate. It's just Q epsilon. And now I can notice that I know explicit shape of phi p, that phi p deformed Q is nothing but Q epsilon over Q for phi p at Q. So then I can just literally substitute this thing into 3-point function and get the following relation, that is u epsilon over q cubed phi p in kind of indeformable theory. So I can kind of additionally deform observables as well, and then I can reuse the answer in original theory by replacing q by q epsilon. But the price is that I need to keep track how to adjust observables to be observables in undeformed theory, in kind of in a theory deform. So and then kind of from this equality we can reproduce this answer identical to this answer. So we just invert this q epsilon over q and move it to the left hand side and get precisely q cubed divided by q squared. Okay, so that is good, and now kind of given this kind of additional knowledge, we can kind of go and compute the non-vanishing 4-point function, which is 4-point function with 4 phi p insertion. So once again, so here we kind of erase that green circle, and here we have. Okay, so since it's my last computation, let me just erase this one and put kind of factor of 3 here. So here we kind of saw that the 3-point function sign invariant. So let me just use this. So now I can erase this thing because we kind of perform a computation, and I have formula on the board. What is the contact term between phi p and phi p? Okay, so now we can simplify our expression. So the contact term part will give us familiar 3-point function in undeformed theory with a factor of 3, because we have like 3 contact terms, 1 contact term for each observer, and this expression equals to 3 times q. So now we also have this derivative term, but for derivative term we also kind of managed to compute the 3-point function. So in deformed theory, this thing is just q times 1 plus epsilon to the power minus 2. So we need to take epsilon derivative of this expression and set epsilon to 0. And here it's cute that the answer is minus 2q, because 1 plus epsilon enters in the power minus 2. So therefore we got the following equality: 3q minus 2q equal to q. And then we can recognize that it's kind of familiar result from Gromov-Witten theory, that the 4-point function of the second cohomology classes, they kind of equal to 1, and this invariant exists in degree 1. So this invariant in Gromov-Witten theory also equals to q. Okay, so we kind of verified yet another prediction from mirror symmetry, that all 4-point functions, because if we have at least one phi I insertion, they vanish on both sides, and for all phi p insertions, we verified that Gromov-Witten result matches Landau-Ginzburg side result. So here we kind of verified mirror symmetry for, okay, so now we verified it for 4-point functions, which is kind of one step beyond matching of quantum cohomologies. Like 4-point functions is some kind of expression which is in general beyond the quantum cohomology. Okay, so apparently we can, in this simple case of CP1 mirror, we can actually do a full verification because, like given that kind of result, that given this Landau-Ginzburg-Saito relation, Landau-Ginzburg-Saito puncture relation, it kind of leaves us with the only possible non-zero correlation functions where we have all kind of observables equal to phi p. So to complete a kind of verification of a mirror for all chromophyt invariants, all we need to do, we need to compute n-point function for this phi p observable. Okay. And we can do it, and kind of it's better to do it in a way that kind of can be further generalized to higher dimensional case by kind of realizing that this computation that we did here is indeed some kind of can be recast in a form of a divisor relation in Landau-Ginzburg-Saito. Like in chromophyton theory, we managed to compute all these invariants by using divisor relation on CP1, by observing that gamma p is actually like hyperplane type of observable, and inserting it, we can kind of eliminate one of such observable and multiply remaining remaining chromophyt invariant by its degree. And degree is 1, so therefore we get like answer 1 for arbitrary number of gamma p's. So let us kind of look at carefully at this computation for a 4-point function and kind of rewrite it in a way that looks similar to divisor relation. Okay, but before that, let us kind of let us first rewrite divisor relation in chromophyton theory. So in chromophyton theory, divisor relation usually works in this type: the gamma p and some other insertions in kind of, okay, so we are writing it in CP1. So degree d is like e times chromophyt invariance of the same degree with kind of one less insertion, with kind of without gamma p insertion. So we can kind of reorganize this invariance into kind of polynomials in Q by kind of multiplying by Q to the power d and taking sum over d. So that will be what we call like without any subscripts. So now in this notation, the divisor relation on CP1, it actually takes the following simple form, that all I need to do to kind of recall the degree d from this kind of degree d expression multiplied by q to the power d is to just apply qd over dq. So if this correlation function also kind of exists in degree d, so it also multiplied by q to the power d, and qd over dq applied to q to the power d is d times q to the power d. And this kind of recasting is somewhat trivial in chromophyton theory, but it's kind of useful in Landau-Ginzburg-Saito theory when we don't have like invariance of a fixed degree, and the correlation function give us like these expressions where we combine the variance of different degrees into polynomials in this Q value. So now having this kind of d over dq applied, applied to correlation function with less observables, so this formula that is just a recasting of divisor relation kind of starts looking like some kind of derivative term in Landau-Ginzburg-Saito recursion. So when Landau-Ginzburg-Saito recursion, albeit we have a derivative term it is kind of not quite a derivative term of the type q d over dq. But we recall that if I shift w to w plus epsilon phi p, then this thing is nothing but kind of w at deformed q. And we can notice that deformed q is q times 1 plus epsilon. And here we can notice the following thing, that applying d over the epsilon derivative to something like q epsilon is the same as applying so kind of okay, so if I have, okay, so we know that the answers in Landau-Ginzburg Saito theory for, say, 3-point function, so they are just some kind of powers of Q. So we computed these powers if kind of sum of the exponents in these arguments is odd, then this power is like half of the power, like half of the power subtracted 1. So, and if you apply like d over the epsilon equals 0 to some kind of power of q epsilon, then we will naturally get something like m times q to the power m. And this thing is nothing but kind of q d over dq applied to the answer in undeformed theory. So therefore, like applying d over d epsilon equals 0 to expressions that only depend on q epsilon, like independent on q, is the same as applying the kind of q d over dq derivative to the same expression in undeformed theory. So therefore here we can do the following thing. So let me erase that part. So we can recast this expression encircled by red into following expression. So it's q d over dq of this correlation function, the W. However, this kind of argument works only in a situation when any kind of coefficients in this expression when they are explicitly q epsilon and not q. So if there is no kind of bare dependence on q. So therefore here we need to kind of subtract additional 3 terms that work in the following way. When q d over dq hit one of the observers, and it can hit like arbitrary observer. Okay, so then, and we still have this term. So then this term is kind of the term that we want. That is the term that we kind of expect for to be present for kind of divisor type of the relation. That kind of 4-point function is related to some kind of derivative of 3-point function. So this derivative essentially picks up like a power of q, which is kind of matched to degree of the corresponding map in Gromov-Itten theory. However, kind of when we turn this epsilon derivative into q derivative, so we still need to kind of undo derivatives on observer, because this trick only works if kind of in observable dependence we also have q epsilon, not q. And because in this formula we kind of have Q dependent, only kind of Q enters into observable and Q epsilon enters in W, so we need to compensate for that thing by including derivatives of observables. So therefore we have two terms, and now we need to kind of see whether these terms would cancel. So luckily they have the same structure. So essentially both of these terms, so they kind of combine into 3-point function for this observable, let me call it phi tilde p, constructed of the following type. So first we take a contrast term between phi p and phi p, and then we subtract 2 d over dq of phi p. However, we in a case of kind of mirror to P1, we know what the contact term is. So the contact term just equals to phi p, and phi p itself is 2 e to the iy. So therefore, q d over dq applied to phi p is again phi p. So we have phi p minus phi p, and that is 0. So therefore here we verified that this observable is 0, and therefore any 3-point function with the 0 observable inserted is 0. And therefore this 4-point function with phi p observables is kind of simply given by this yellow expression, which is just q d over dq derivative of the 3-point function. So that is just kind of recasting the computation that we did before for a 4-point function, recasting it in a form that looks like a divisor relation. So now, after we recasted it in a form of divisor relation, we can see which parts could be further generalized. Okay, so here it's kind of a bit more challenging than puncture relation, but still manageable. So let us kind of first generalization is try to go to kind of higher dimensional Landau-Ginzburg side theory. So in higher dimensional theory, the story is more complicated because you kind of may have several kind of hyperplane generators of H2. So in high dimensional theory, so this thing is not phi p, but some kind of phi that corresponds to some kind of one-carat dual of some hyperplane that is one of the generators. So it will be some H alpha. So now, kind of when we introduce Qs, we kind of introduce one type of Q for every generator of H2. So therefore here we will have like Q alpha that corresponds to this H alpha. So therefore we will recast like shifting W by phi H alpha into kind of logarithmic derivative in Q. So essentially, like mirror superpotential, we will see it will contain a term like Q alpha phi H alpha. So therefore, shifting this term by epsilon is kind of like probing it by Q alpha d over Q alpha derivative. So here, and we have no summation. So here. So no summation over alpha. So kind of for fixed alpha, we perform Q alpha d over dq alpha. So that is kind of our derivative term. So then once again, we need to compensate for the fact that we only deformed W and didn't do anything to observe. So therefore we need to kind of subtract a possible kind of Q alpha dependence for observables. So similarly here, it will be contact term with some kind of observable okay, so now it's not 3, it's like 3 terms. And then what we will end up in the following in kind of in a linear okay in a sum of the 3-point functions with kind of observables phi alpha tilde that are constructed in the following way. So we take kind of our observable phi alpha, we compute a contact term. My bad. I have like I can't go to think better. Let me explain it how it works for phi 1 and for phi 2 and phi 3. It kind of works in an analogous way. So for phi 1, we take the contact term of phi 1 with phi h alpha, and we want to subtract kind of Q alpha dependence of phi 1. Okay, so that is kind of a terms that gives us a kind of difference between 4-point function evaluated using Landau-Ginzburg-Site recursion and just kind of simple derivative of 3-point function. Simple derivative of 3-point function with respect to Q alpha that correspond to this H alpha. This H alpha is some kind of element from second homology space. And so now the kind of non-trivial thing to show is that that kind of if I here eliminate 1, that for all phi that are from image of a good section, so this kind of difference between contact term with H alpha and the contact term and this Q alpha d over Q alpha derivative, that this thing vanishes. So I don't have like argument how to do it in the most general setting. So what I know that at least for kind of projective spaces, like if I'm looking into mirror for Pn, so then I can kind of explicitly write down like image of a good section and just verify that for every basis element from image of a good section that this equality holds. So, okay, for projective space and actually for product of projective space. So in this case, I can kind of write down in some rather explicit form like this phi h alpha and then just verify that for image of a good section this condition holds. So there might be some kind of better way of justifying it for mirror for any toric, but I don't know it for now. So what I know is that I can explicitly verify this property, and by verifying this property, I kind of completed a proof of Landau-Ginzburg-Site divisor relation for a 4-point function. So for a 4-point function, like for a mirror Landau-Ginzburg-Site theory to product of projective spaces, we have also divisor relation on Landau-Ginzburg side to side that matches with divisor relation on Gromov-Witten. So in the case of, I think in the case of P1, in the general case, like this construction can be kind of immediately generalized to endpoint function, because the procedure is kind of very similar. So if here I have like more observables, so phi 1, phi 2, phi n. So then what I have? So here I also have more observables in the derivative term. I have like more observables in this term in the contact term. So I have exactly n contact terms, and then I can perform sort of the same trick as before. So first I turn this epsilon derivative into q derivative, and the price to do this will be kind of subtracting q over dq alpha applied to each of the n observables. And I have exactly the kind of similar type of phi tilde observables, which is like a combination of a contact term from Landau-Ginzburg side recursion and this derivative term for kind of compensating difference between a red and yellow expressions. And once again, once I proven that this equality holds, it kind of holds for inserting it in any kind of endpoint function. So its endpoint function is also linear in all arguments. So if one of the arguments is literally zero, so then it once again vanishes. So therefore proving it once kind of allow me for immediate extension of this divisor relation to any kind of endpoint function. So and that gives me a generality of divisor relation from Gromov-Witten theory. So and that completes a kind of our verification for a mirror for a P1. So for a P1, we kind of showed that Landau-Ginzburg side theory, it kind of contains a puncture and divisor relation when we insert phi I and phi p, and this puncture and divisor relation, they have exactly the same structure given the map of Gromov-Witten invariance to Landau-Ginzburg side correlation functions as in Gromov-Witten theory. So therefore, the moment we match it 3-point functions, then we can use puncture and divisor relation to get all Gromov-Witten invariants on P1, and then similarly we can use puncture and divisor relation Landau-Ginzburg side theory to generate all correlation functions, all endpoint correlation functions from a 3-point function by kind of recursively applying puncture and divisor relation. So that kind of completes verification of a mirror.
Excuse me.
Yes.
Here in the Landau-Ginzburg cycle side, these relations are by definition.
Recursion relation by definition, but the relation where in the right hand side instead of this derivative, like red derivative, is kind of canonical part of the definition. But then I want to replace red term, by another derivative term, orange term, that looks like a divisor relation. So, and for that I need to pay a price, because I need to subtract like action of these derivatives on observables. And then kind of I have this extra term of turning red expression to yellow expression, and I still have contact terms from a definition of Landau-Ginzburg side recursion. And then to get a divisor relation, I need to kind of independently verify that these two terms exactly cancel. So it means that for every kind of element of good section, which is among these n observables, I have this property that a contact term with any element of good section and h alpha is exactly equal to kind of logarithmic derivative with respect to Q alpha of the same observable.
Yes, but so this identity depending on your construction.
Yes, so this last identity, it depends on many factors. So because contact term depends on the choice of a good section. So that depends. And then kind of the structure of phi's also depends on the choice of a good section. So that's why I said there is no, at least I don't know, like a universal way of verifying it without explicitly writing a good section in some cases.
So this is the condition you need to impose when you
That's the condition I need to verify, to claim that a certain that Landau-Ginzburg side recursion with respect to observables mirrored to hyperplane gives us a divisor relation. So that statement holds if I verify that this orange, let me call it orange conjecture. Orange is a conjecture, and I kind of managed to prove this conjecture. Well, it's proven, or in this specific setting when X is the product of projective space. But I kind of strongly believe that this conjecture holds for any toric variety, but I can't prove it. So that's why, for now, modulo this conjecture, I managed to kind of derive divisor relation in Landau-Ginzburg side of theory from Landau-Ginzburg side recursion. Modulo this conjecture. So it's not kind of additional assumption, it's a conjecture that was proven in some kind of family of cases where I can like literally construct all the terms and just evaluate the difference and see the differences here.
So it depends on how to construct the superpotential and how to construct phi.
Yeah. So for now, at least without having a general proof, so the verification of this conjecture seems to depend on all details of my construction. So which is kind of not what I want, and hopefully, if I get like some better proof in the future, then it will be somehow insensitive to like tiniest details of construction. But I have what I have for now. So, and that is somewhat different from puncture relation, because for puncture relation, like the vanishing of a contact term between identity and phi was kind of insensitive to any details of the construction. It was like more or less by definition of a good section that the contact term of a good section with identity is always zero. So in that sense, kind of puncture relation is kind of more robust construction that it's kind of works automatically. But here, I really need to go all the way down to rewriting in some explicit coordinates like phi and phi h alpha and evaluate both terms for some family of mirror superpotentials to show that it is indeed zero. Yes, so that check by computation that I kind of perform computation, and that is somewhat not very satisfactory for now, but hopefully I will improve later. What?
Which is toric right over simply cube over a cube.
Okay, I'm not familiar with that. Sorry. Yeah, so I think probably it's somewhat tractable to verify this equality for kind of arbitrary toric arbitrary toric surface. It's like two-dimensional, complex two-dimensional toric variety. So I think that is also doable. But for general kind of toric variety, I need somehow additional insight of how to do this computation. Okay, so
excuse me. Yeah. So the superpotential W is unique in this construction form.
Yeah, superpotential W is kind of
SW is not unique, right?
No. So XW what is it?
SW.
Yeah. So no. Okay, for SW, I don't know whether it's unique. So that's kind of the story. So what I know like two statements from a literature. So if I use kind of tropical mirror construction that we will get into hopefully in the next couple of lectures. So tropical mirror construction give me a very unique SW. So that we call like tropical good section. So it kind of follows as a part of a mirror map that you not only get W but also get like SW of some particular form. But there is a kind of a theory of a good sections for just kind of random W. So you kind of forget about mirror relation. You just study Landau-Ginzburg-Saito theory with some superpotential on some kind of manifold X. So that is also was done by people. So people studied, say, polynomial superpotentials on X, which is Cn. And also asked the question whether there is like a unique good section or there are multiple good sections. And I think there is kind of no conclusive answer. So in the case of a single variable, yes, there is a conclusive answer that for a single variable, good section is unique. But the moment you add like 2 or 3 more variables, even in polynomial setting, then kind of answer is unknown, whether there is like a unique good section or there are multiple good sections. So, and that kind of raises an interesting challenging question, like if on a P side, I say have multiple good sections, like is there some kind of distinct feature of a tropical good section that kind of comes together with a mirror map?
So the tropical good section means give a cohomology class we will correspond.
Yeah. So we will kind of start with a cohomology class, then we will put into some kind of duality machinery, and as output get a particular holomorphic function constructed from this cohomology class, and that's what we will call tropical good section.
Okay.
But I'm kind of still haven't got there, but there are like some definition of a good section, like some defining property, that it is section with this and this property. So that was kind of formal definition of a good section in Landau-Ginzburg-Saito. And for this kind of for section satisfying this definition, it is kind of not known whether they're unique or not. For this kind of exponential superpotential that emerge from a mirror symmetry.
So in general, Landau-Ginzburg theory will also have this recursion.
Yes, so in order to define recursion, it is sufficient to choose any good section. So good like good section, like good property of a section is essentially equivalent to additional requirement that you get restored symmetry in all arguments. But to define Landau-Ginzburg-Saito recursion, it's just sufficient to have any section, because any section will define you a contact term. And therefore you can, in principle, define recursion with any section map. But then this recursion may not give you a symmetric correlation function. So if you then require that the correlation function tell the recursion asymmetric, that imposes additional conditions on your section. And these conditions, they are kind of equivalent to definition of a good section given by Kyoji-Saito in kind of study of singularity theory. And that Kyoji-Saito's good section from singularity theory is not known whether it's unique or not. And any kind of good section would give you a perfectly healthy Landau-Ginzburg-Saito theory in a sense that it will give you well-defined correlation function that are symmetric in all arguments. However, it is not known whether like any choice of a good section would give you the same correlation function. So that part is not known. And what we know from mirror symmetry construction, that we know at least one good section that kind of we derive it from a mirror that satisfies Kyoji-Saito requirements for a good section, and that gives us correlation functions in Landau-Ginzburg-Saito theory that match Gromov-Ito invariant. So that's what we know. And what we don't know, whether there are alternative good sections, and what is the significance of the answers in Landau-Ginzburg-Saito theory computed using alternative good sections. whether it's the same as the one with the mirror the same as a mirror computation, different from a mirror computation. So that is kind of unknown beyond the single variable case. So for single variable, yes, everything is kind of unique and simple. But for multiple variables, you kind of run into unknown territory. And that is kind of interesting research question to which I unfortunately don't know the answer. Yeah, I think we just got like 7 minutes before the end of the lecture. So I think there is no point in kind of starting higher dimensional Landau-Ginzburg-Saito theory. That we will do next time. But let me kind of do one sort of preparational computation that kind of another illustration on the kind of importance of choosing like particular observables, not an arbitrary function from classes in Jacobian. So let us look at what happens to the 4-point function. So let's say we have phi 1, phi 2, phi 3. And we shift one of the observables, so say phi 4, we change it to phi 4 prime, which is phi 4 plus, okay, one-dimensional vector field, okay, v, okay, function, v times w prime. So then the change in our 4-point function will be given by this kind of 4-point function. When we have one of the argument is just kind of not zero representative of a trivial class in Jacobi ring. So this thing belongs to kind of trivial class, but it's not trivial representative. So the question is like, what is this expression? Whether it's like 0 or non-zero. And if it happens to be 0 for any choice of phi 1, phi 2, and phi 3 from a good section, so then we would say that 4-point functions also descend to classes in Jacobi ring. That they are insensitive on kind of choosing representative in a class. But if it happens to be non-zero, so then we need to kind of pay attention to which functions we insert into this correlation function. Okay, so let us once again apply Landau-Ginzburg-Saito recursion to this expression. So we will have two types of terms. So we will have a term that kind of contain contract term between v times w prime and phi a. Okay, phi 1, phi 2, phi 3, and plus two more terms of the same sign. And we would have like evaluated 3-point functions evaluated with undeformed double. And we have yeah, okay, so sorry, not too terms. I need to be more careful with that one, because so here I do a recursion with respect to phi. So that's why here this term will be something like phi 2, phi 1, bw prime phi 3, and kind of one more term where 2 interchange this 3. So this kind of among 3 terms, there are 2 types. When it's a contact term between vw prime and some phi, and a contact term between phi and phi. And then we finally have a derivative term where we have phi 2, phi 3, and vw prime in the deformed superpotential deformed by phi 1. So that is kind of definition, applying Landau-Ginzburg-Saito recursion, and that is recursive definition of our 4-point function. Okay, so now let us analyze this term by term. So first, let us look at this term. So this term has the following structure. So it is some kind of phi, okay, some kind of function, not necessarily from a good section. So that's obtained by computing contact term v times w prime phi 3 and 3-point function in kind of theory with undeformed supremum. So this term is zero because in our definition of a 3-point function, we kind of take a residue using kind of poles of zeros of w prime. And here one of the observables is immediately proportional to w prime. So v is just some kind of holomorphic function, so it has no poles. So therefore inserting here w prime in 3-point function gives us 0. And that is not surprising because 3-point function was defined on classes. And here we just inserted like representative of a 0 class. So it's good. So we managed to eliminate like 2 terms out of 4 terms. So maybe kind of this 0 is not as hopeless as we thought. Okay, so now what about quantity?
Excuse me, do we need this CW term to be in the image of good section?
No, for this we don't need. It's like 3-point function. So for 3-point function, it's defined on classes. So that's why we don't care whether it's an image of a good section or not. So now 2 more terms. So let us kind of look at this term. Let me. Let us compute the contact term between kind of element of a good section and v times w prime. So in one-dimensional setting, what we need to do, we need to multiply these terms, and we need to subtract a kind of good section, apply it to product of these classes. But with w prime is 0 class, and 0 class multiplied by any class is 0. So therefore it's kind of SW applied to 0 class, which is 0 itself. So therefore here, this term is just 0. And once again, a numerator is divisible by w prime because it's proportional to w prime. So it's v pi times v prime. So now what about this last term? The last term we can also simplify. So w prime and here pi 2, pi 3 computed in deformed theory by epsilon 5. So let us do the following thing. So let me call this kind of temporary w tilde. So if I have 3-point function in w tilde theory, if I have some kind of v tilde, w tilde prime, and a kind of any other 2 observables, so this thing vanishes. So for the same reason that this one is representative of 0 class, and 3-point function defined in class. So let us kind of turn this expression in a following way. So let me kind of add and subtract epsilon phi 1 prime term. So if I add it, phi 2, phi 3, so I kind of add it, and I need to kind of subtract it. So it will be v epsilon phi 1 prime, phi 2, phi 3, evaluated at w tilde. Okay, so now this term is 0. So that was kind of our idea of adding and subtracting. So now this term, so epsilon is independent on y. So this term is itself proportional to epsilon. So therefore here, when we apply this derivative d over d epsilon evaluated epsilon equals 0, so this d over d epsilon derivative applied to this term. So there are like two places with epsilon dependence. So it's overall epsilon here and epsilon dependence in W tilde. So when you apply kind of d over d epsilon evaluated epsilon equals 0, so if this derivative hits W, then the whole expression vanishes because it's proportional by epsilon. So the only way to make epsilon d over d epsilon of this expression is not 0 d over d epsilon equals 0 is to kind of hit and eliminate this epsilon. So therefore here, from this derivative term, okay, so let me replace this contact term we already computed with phi 1 v whole prime. And for this term, all we get another 3-point function, which is of the following type. So it's here, this argument is minus v phi 1 prime, phi 2, phi 3, and we set epsilon to 0 after we take a derivative. So we see that these two terms, they kind of almost identical. So we kind of compare them. So we need to kind of, so accept these expressions in red, the rest of the expressions identical. But for these expressions in red, they are not quite identical. And the difference is that here we take a derivative of a product, and here we only take a derivative of phi 1. So therefore here, the difference of these two terms will be proportional to derivative of v multiplied by phi 1, phi 2, phi 3. So that is a universal formula for kind of what happens, so how the 4-point function changes if I change the representative. So if I here kind of insert an element from a 0 plus that depends on v, then the answer kind of is non-zero unless v is constant. So if v happens to be a holomorphic function that is constant function, so then the right hand side is 0. But if I shift my observable by v times w prime for non-constant v, then generally the answer would be non-zero and will be sensitive to derivatives. And this formula is also kind of has some deep meaning in the sense of gravitational descendants, but we will kind of reuse this formula next time when we will talk about like non-uniqueness of contact terms. Okay, so I still have it. So we see that non-uniqueness of contact terms is some kind of okay, so for now it's okay. Okay, so we will see next time how this formula encircled in orange that we derive it in one-dimensional case. So we will derive generalization of this formula to higher dimensions and see how this formula helps us to kind of control non-uniqueness of contact terms. So essentially, non-uniqueness of contact terms will be kind of expressions of this type. So the contact terms are kind of well defined as a classes in Jacobi ring. So it means that as a holomorphic functions, they can differ by some kind of expressions like this, but higher dimensional version. When you have something like vkw, and kind of we will see that there is a high dimensional version of this formula where instead of v prime you have like something like holomorphic divergence of a vector field. And we will see that the vector field that kind of emerge due to non-uniqueness of contact terms, that they are actually holomorphic vector fields that are divergence free. So although contact terms will have this ambiguity, but it wouldn't affect correlation function because vector fields are divergent. But we will discuss it in details next time. So today I just wanted to kind of give you some kind of hint on where are we going. So today we kind of discussed in details one-dimensional version, like proven almost everything except like symmetry of correlation functions. So we kind of indirectly verified symmetry by verifying mirror relation, but we haven't proven symmetry like using purely Landau-Ginzburg Saito setting. So that we also do next time, and next time we will talk about this kind of problem, potential problem with non-uniqueness of contact terms and its solution due to kind of relations of that type, which allow us to kind of control this non-uniqueness and verify that it is kind of non-uniqueness that essentially not problematic because it's non-uniqueness with some divergence-free vectors.
You mean it may not be zero?
Yeah. So here it may not be zero if vector field is not divergence-free, but we will see that non-uniqueness that is non-uniqueness for CW is of this type, but with divergence-free vector field. So that this kind of special situation that normally you would say the answer is non-zero, but our non-uniqueness is kind of more special than a general element of Jacobi ring. It's kind of element of Jacobi ring with additional condition on V. So and this additional condition on V and kind of formula like this generalized to higher point correlation function allows us to show that this non-uniqueness exactly vanishes in our construction. Yeah, and I think that is what kind of was missing in the works of Kyrgyzstan, because he studied like these contact terms like modular, like contact terms like restricted to classes in Jacobi ring. So that's why like, he didn't write a recursion formula because there was like immediate problem with recursion formula if you kind of observe that it's not well defined on classes and your contact terms only define it like modular element of Jacobi. And then kind of our observation with Andrei Lossev was that even though you have kind of terms proportional to elements of Jacobi ring, they are more special than general terms. They have this divergence-free vector fields, and that is enough to make a recursive procedure well defined. Yes, so sorry for going over time. So I will post. So I posted like homework 1, which is due Friday, which is mostly homework on doing Gromov-Witten theorem P1 cross P1. And I will post kind of homework 2 also later this week, which will be focused on Landau-Ginzburg Saito theory with a single variable, but with polynomial superpotential. So that is kind of also a tractable class of Landau-Ginzburg Saito theories with interesting answers and even with some applications to mirror symmetry. So that's why I encourage you to kind of try to do homework that kind of gives you some additional useful examples and statements in the mirror symmetry. Okay.